Yeah, comes on everyone. Let's. Oh. Let's go ahead. We are starting with wave optics. Hope everyone has gone through the notes. It's important because if you see wave optics, right, meaning the basics are like, there are two to three things which you should definitely know. And rest of it, right, everything just keeps coming from the same thing, especially the YDAC part. So if anyone is not clear about YDAC, you should definitely go through the notes and check it out. Anyway, I'll just still try to brief it up a bit. But revising the notes before coming to the class is important. That will help you, or else everything will feel like, something weird. Why is this not loading now? What happened to this? Let's get we'll start off with this. I hope you guys remember we have done something similar in mains curve vision also. Wavefronts. Yeah, this thing. So what is the idea here? See, so in a wavefront, right? So whenever you define a wavefront, it is simply the locus of all the points which are in phase. So that is the definition of a wavefront. So when a wave travels, it will, it's emitting different waves, or different from a source, you get different waves. So if you take all the points which are in same phase, so they should have same path difference. And if you combine them, what you get, the shape is called a wavefront. So the proper wavefront, the light rays will be always perpendicular to the wavefront. So this is how the things will be there. So if this is the wavefront, then the rays are going something like, basically they're getting, it should be always perpendicular to the wavefront. Now looking at this picture, so whenever you get questions like this, first convert it into ray optics and then get back the problem. For example, look at this. If you're sending a plane curve, that means the light rays are coming parallel. So if you send parallel light rays, what will happen? They will meet at the focus. So if the light rays are meeting at the focus, so how should this wavefront look like? So this wavefront should look like this. This is right. What about this guy? If you send light rays parallel to this lens, again, so they will meet here and then they will diverge. So that means here the wavefront should look like this, isn't it? So this is wrong. So that is how you check basically. So when you send parallel light rays again here, they will try to meet at the focus. So here the wavefront should look like this. Yeah, that looks nice, right? And what about this thing? That is a lens converging. No, sorry, that is not it. So it's actually converging. It's like this. So this is also wrong. So when the wavefronts go here, they converge here, and then the light rays will go off like this. So basically here the wavefronts are like this. So they're converging, so they have to become small, and then they'll expand again. So it should be like this. So this is right. So C option. Clear with the wavefronts, how to draw? So the main idea here is whenever you have a wavefront, so think of it like this. If the light rays are coming from here, the wavefronts will be like this. They're emerging and they're becoming bigger and bigger. If light rays are converging at a point, the wavefronts will be reversed. So they'll become smaller and smaller. So you have to enclose them. Hope all clear with this. So yeah, it doesn't matter. Thick lens, thin lens, end of the day, they'll still converge. So this is another one. Let's say we have three sources, S1, S2, S3. We have a point P here, and let's say intensity of this source is I, and this is 4I, and this is 9I. S1P minus S2P is lambda by 4. No, maybe let's say lambda by 3. S3, S2P minus S1P is lambda by 6, and S3P minus S1P is lambda by 3. So we have three sources, so it's an interference due to three light sources. Find the intensity at point P. In YDSC, you're doing, interference due to two sources. What will you do if you have to do interference due to multiple sources? So here I gave you the path differences already. So we have three sources of intensity I, 4I, and 9I, and there's a point P, and these are the path differences. S2P minus S1P is lambda by 6. S3P minus S1P is lambda by 3. Find the intensity at point P. So wave optics, right? The chapter is, it can be hard, but if you know your standard results and the basic models, right, you can handle most of them. So if you see entire wave optics, primarily there are three things. One is your YDSC, one is the interference on thin films, right? And I'll show you one more thing, finding number of maximas and minimas on a screen. So the thing. How do you handle this? I hope everyone has derived, last class, whatever I taught you, you derived on your own. That is important. If you just read them, nothing will happen. Please try to derive them again own. So the last thing, that pseudo force, Coriolis force, all that stuff. How do we handle this? So if you have multiple sources, do you guys remember phasors? We have to use phasors. The first time you heard this word phasors was in simple harmonic motion, SHM. Then we have used it extensively in different things. So let's say start like this thing. So this thing will be Y1, which is, so that the first source will be A sine kx minus omega t. Y2, that's the second source, intensity, when it reaches there, it is kx minus omega t. So this will give you a phase difference. How much? 2 pi by lambda delta x. That would be pi by 3. And this will give you a phase difference of 2 pi by 3. So this would be pi by 3. So the third one, the source, when it reaches point P, the equation becomes y is equal to a sine kx minus omega t plus 2 pi by 3. So the intensity at point P is actually the resultant of these three waves, y1 plus y2 plus y3. How do you add three sine functions which are looking like this? Wait, I did a mistake. And we also know intensity is proportional to amplitude square. So this amplitude must be 2a and this amplitude must be 3a. You're getting it? The all don't have same amplitude because your intensity is proportional to amplitude square. So S1 ka amplitude will be a, this will be 2a, and this will be 3a. Is everyone clear with these equations? So the reason why we got this pi by 3 and 2 pi by 3 is because of the path difference. Because they are traveling different distances, it creates a phase difference between the two waves. So if you take S1 as 0, compared to that, S2 will have pi by 3, S3 will have 120 degrees ka phase difference. All clear with that? Yeah, most of you got the answer. It was the same question which we did in the class notes. It's a good one. Right? And then how to add these three things? When you want to add them, we use phasors. So what does a phasor do? A phasor ka logic is this. The amplitude behaves like the vector ka magnitude and the phase angle behaves like the angle of the vector. So y1 ka angle is A, angle 0. So vector 2a ka vector, angle 60 degrees. 3a ka vector, angle 120 degrees. So you treat them as three vectors. Resolve them into I cap, j cap. You end up with a plus 2a cos 60 minus 3a cos 60. This will be 2a sine 60 plus 3a sine 60. Then get the resultant of these two vectors. That will be your a resultant. You can solve this. So then you can write the final vector yp will be a resultant, and let's say this angle is alpha, a resultant into sine kx minus omega t plus alpha. This is how you can add actually three different sine functions. As long as they're same frequency, you can use this logic to add up the functions. So what is the intensity proportional to? AR square. So you can solve this. I think you will get intensity at point P 99. So there I skipped the steps. You can solve this, and the detailed solution is there in the class notes. You can check it out. But I hope you got the idea how to add the phasors. So anyone who has no idea about this phasors should definitely go to the SHM notes, and that is the first time we introduce this. Quite an important concept there, phasors, page 33. How to add two sine functions with different amplitudes. They should have same frequency though. Then I took a lot of examples, so you can check it out. Page 33. You need to know this thing. So if you have more than two sources, this is how you handle them. Every time you won't be so lucky to get a, that YDSC thing. We got a screen here. We got a mirror here. I know they kind of look same, but yeah. We have a source here at a distance small d, which is equal to 3 lambda. This is capital D, and D is much, much greater than small d, right? So this is the source, and there'll be an image. So find the position of maximus on the screen. Let me ask you like this. Find the number of maximas and find the position of second maxima, something like that. Let me ask you this only. Find the position of maximus on the screen. Screen is very long, plus to minus infinity. The wavelength of the source is also lambda. So remember, interference happens between sources which are in sync or which are coherent. And how do you create coherent sources? Two different light bulbs can never be coherent. So you have to create a second source, either using the same source, either by reflection or prism or something like that. So here the source and the image will behave like two sources. These two sources will have an interference on the screen. So find the position of maximus on the screen. Now in YDSC, the sources used to be like this. The sources are like this, S1, S2, and this is the screen. This is different. Here S1, S2 are like this, and the screen is perpendicular. So this is a variation of that Vaidesika thing. If it was a mains question, right, they would ask you find the number of maximus. That would be an easy question. Finding the position requires little work. There's a small trap, huh? Not a big one. I hope you realize, but let's see. If you goof up, that is also fine. So there is a certain mathematical approximation you should know. So in case you don't know, I'll show you an approximation. See, if you have two sources, A and B, this thing you learned in dipole moment actually. And let's say you have a point which is very, very far. So from the center, if you have a line like this, what you can do, you can extend the line. So from B, we can drop a perpendicular and we can call this B dash. And from here, we can drop a perpendicular, we can call this A dash, right? And if this angle was theta, and if this distance was d by 2, and this was distance was d by 2, this guy will be d by 2 cos theta. And this will be d by 2 cos theta. So here the approximation is, when if this guy is very, very far, if r is much, much greater than d, we can say AP minus BP is approximately equal to A dash P minus B dash P, which is nothing but A dash B dash. That becomes d cos theta. It will be quite a useful approximation. Clear with this. So there's another way people do this thing. You can do like this also. A to B. This is the point P. Again, P is very, very far. You drop 2 points here. And then they argue, you drop a perpendicular here directly. This is D. Anyway, the angle will be almost theta only. So this would be d cos theta. So from here also you can argue that AP minus BP is d cos theta. So you're assuming basically this length and this length are equal and the extra length is d cos theta. Both are right, because as long as you approximate right, everything works. So you see which one you like. Both are fine. End of the day, that this will be d cos theta. This, you should know, this approximation comes a lot. So you'll need that here. So that is the reason I gave d is much, much greater than small d. Wave optics is one chapter we should definitely, go through the notes and be thorough with it. Like I said, EMI, magnetism, AC circuits, wave optics, rotational mechanics, modern physics. These chapters are very important for advance. They can really play around a lot. They can twist things. They can give weird things, paragraphs. And it is good thing. If they give you some weird paragraph, don't be scared. You should be happy, because it's a weird paragraph. Once you read, it feels really scary. But even they understand, they don't expect you to really learn and solve. So they give the questions easy. That is something I noticed. The more weird the paragraph is, out of 2 questions, 1 question will be dead easy. You can just read the paragraph and explain. So if you're good in physics, the paper should be tough. Simple thing, because if it is easy, then everyone will start scoring. So you might score 90 out of 100, but if the average is 70, what is the point? If the paper is tough, you might score 60, but the average is 10. That is what you want. That difference, not the score. So to get a good rank, you should do well, and others should mess up more. So now others messing up is not in your hands, but all you can do is do your work. So how do we handle this? Listen, I'm not sure whether you got the first trap. So S, and you'll get an image here, I. So this distance will also be small d. So if you take any point P here, one light ray will go from S to P directly. One light ray will go from reflection. So it gives you a feeling as if it is coming from I directly. But whenever a light ray reflects on a mirror, you get an extra path difference lambda by 2. I hope you guys remember that. So that is one thing. If you forgot that, the whole thing will go for a toss. So if you have a mirror, and when you bounce off a light ray, if this light ray ka phase is 0, this phase will be pi, or the extra path difference will be lambda by 2. So if you guys remember, there are 3 ways you can create path difference. 1, you make them travel different distances. 2, make them reflect on a mirror. 3, make them travel inside a slab. I hope you getting this thing. So there are 3 ways you can create path difference. Make them travel different distances, hit them on a mirror, or make them travel through different slabs. That's it. These are the only 3 ways you can create a path difference. Once you got the path difference, the story is always the same. Delta x is equal to n lambda, maximum, minimum, and everything. So it's always about the distance. So your question has become like this. So we have an I and we have point S, and we are trying to find a thing here P. So what do you want to find? The path difference. So what is the path difference? Delta x will be IP, but don't forget IP plus lambda by 2, because you got a path difference because of reflection. Minus SP. Right, and you can take this angle to be theta, and you can drop a perpendicular here, and you can assume this is also theta, which is not true, but again, like I said, they're so small you can ignore that, and this extra path difference will be d cos theta. So IP minus SP is equal to d cos theta. There, so we'll get delta x is equal to d cos theta plus lambda by 2. This is the path difference of any point on the screen at point B, which is making an angle theta. Clear with this? So once you got this, what do you want to find? You want to find maxima, minima. So delta x is d by cos, d is how much? 3 lambda cos theta plus lambda by 2 is equal to n lambda. This is for maximus. Great. So if I put n is equal to 0, that is your central maxima. What is the definition of a central maxima? The point where the light rays travel, they have equal parallel or equal path differences, or the delta x is 0 is called central maxima. How much is this? So we will get cos theta is negative. So yeah, this thing doesn't exist. Getting it? Theta can't be negative there. You have just taken an half angle from the top. So there is no central maxima here. Then put n is equal to 1. Then 3 lambda. I'll show you a better way. Like, you can even think of this thing in another way. Is equal to lambda. So yeah, from here you'll keep getting cos theta ka values. So yeah, that will be n minus half. Lambda will cancel by 3. So put n ka different values, you'll get everything. And cos theta ka value must be equal to less than equal to 1. So n ka value will be 3 plus half, so 3.5. So there is a limit. I think I forgot it too, I guess. Clear with this? Nee, I did a mistake. Wait. This is 6 lambda. That was a mistake. Because this is d and d, no? That is 6 lambda I should take. Then this would be 6. Then 6. So n will be less than equal to 6.5. So where are these numbers looking like? So this is the source. This is the image. So when you go here, see, just put there, put theta is equal to 0. If I put theta is equal to 0, what will I get? I will get 6 plus half, na? So if you put theta is equal to 0, I'll get n is equal to 6.5. This is a minima. This is not a maxima. If n is an integer, it is a maxima. If n is 6.5, 7.5, it is a minima. Right? And then that means somewhere here you'll get n is equal to 6. And if you put theta is equal to 90, theta tending to 90, then n will tend to half. So this n ka values, right, are lying between half to 6.5. So somewhere in the middle, you'll have n is equal to 5. You have n is equal to 4. You have n is equal to 3, and n is equal to 2, n is equal to 1. Clear with this? You're getting, similarly, you'll get one more n is equal to 6, you'll get n is equal to 5, you'll get n is equal to 4. The numbers will repeat here. You know why you get numbers like this? That is because if you see this on a 2D screen, think of like this. If you actually look at this on a screen, the two sources which you have S and I, when you take any particular point here, this is not a single point, isn't it? This entire circle will have same path difference, isn't it? So this n ka values which you are getting are actually circles, you know. So this center circle is n is equal to 6.5. Then you have a circle here. This is how the fringes will look like. This is how the pattern will form. This is not the exact picture, but it would look something of this sort. Not the exact one, but you will see something of this pattern. Can you see the rings? You will see bright rings, dark rings, bright rings, dark rings. Okay, this is not exactly right. This is actually diffraction ka pattern. Beach may should get a dark spot. Getting it? So kind of, it looks like this. So that is the reason the numbers are repeating. So these are actually fringes. Is this clear, everyone? Now here you have to be careful, okay? There's a small thing. They'll ask you like this. Find the maxima, find the second maxima closest from the center. Look at the word, huh? Find the second maxima closest from the center. Means which maxima they're talking about? So people will think n is equal to 2. That is the way people get trapped. Find the second maxima closest from center. So the second maxima closest from center, this is your first maxima, this is the second maxima, isn't it? That means he's talking about n is equal to 5. Clear? So just be careful with the terminology, the words. All got this thing. Do you guys remember how to find the number of maximas on the screen? That is more simpler thing. Listen to that also. Suppose if you have a screen, if you just want the number of maximas in this question, S and I, this thing already has a path difference of lambda by 2 because of reflection. Okay? This is what you do. Send the light rays parallel like this. What is the path difference? Lambda by 2 plus 6 lambda. So 6.5 lambda. Then send the light rays parallel like this. So at infinity, the path difference delta x is half. So the logic is this. If this is half here, that means n is equal to 1 will be somewhere here, n is equal to 2 will be here, n is equal to 3 will be here, 4 will be here, 5 will be here, 6 will be here. Similarly, 6, 5, 4, 3, 2, 1. So how many you have? 1, 2, 3, 4, 5, 6, 6. They have 12 maximas. Is that making sense? If you just want the number of maximas, this is the fastest way to calculate. All sure with this? Clear? So using this logic, let's do this question. This also we did in the class notes, so a good one. So we have a screen here. We have one source here, S1. We have one source here, S2. Let's say this distance is 5 lambda, and let's say this distance is 12 lambda, right? And this is perfectly absorbing material. So light will not bounce from here. This is a perfectly absorbing material. So we don't want light to bounce off the material here. Okay, and the screen is very, very far. Okay, this is very far. Find the number of maximas and minimas on the screen. And you can even find the positions, but yeah, let's get the number of maximas and minimas on the screen. So every time they won't be in a line, you can clearly see here this line and this thing. Can you see? Now they're at an angle. $18 is what? Maximus or minimus? Okay, minimus. $18 maximus, okay. $18 maximus, 17 minimus, 26 maximus, okay. So first thing, the light rays which are going like this, these are the last light rays, isn't it? After this point, there are no more light rays. Do you agree? S2 might give the light rays, but S1 ka light rays will not come there. That means this is the last point where you'll get a interference pattern. Below that, there is no pattern. Clear with that? That is one. So what is the, so before that, let me define something. Let's define delta x properly. Let's define delta x as S1p minus S2p. This is important. Previously, you didn't have a problem, but now you will have. So what is the path difference here then? Delta x, this will be 13 lambda. Agreed? Now, if the light rays are going straight like this, at infinity, path difference kya hoga? Again, remember it is S1p minus S2p, but S2p is traveling more. This is minus 5 lambda. Making sense? S1p minus S2p. And yeah, similarly, you can also say at some position here, they will travel equal distance. So this is delta x is 0. So you can clearly see the numbers. They're going from minus 5 to 13. So what are the numbers here? So you'll somewhere he'll find minus 4, minus 3, minus 2, minus 1, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, and 13. These are all the maximas. Is that making sense? And where are minimas? Minimas will be between them. Minus 4.5, minus 3.5, all these are minimas. Minus 2.5, minus 1.5, minus 0.5, plus 0.5, 1.5, 2.5, 3.5, all these are minimas. Sure, how to calculate this? So what is the final answer? 18 maximas and 17 minimas, right? I don't know, someone typed, I'm just putting it. But is the process clear, everyone? Both are 18, 18 kya? So check kar lena, I didn't count, you see whatever it is. Clear with these calculations. So remember that is minus 5 lambda, it is not plus 5 lambda because it is S1p minus S2p. Now you might ask, sir, why didn't you do this before? Here we didn't have a problem actually because this and this and this, they're all same distances, right? So here we didn't have a problem here. That's why it is both plus on the top at the bottom. This is plus, this is also plus. Everyone got an idea what we did? Let's see one more like this. This is not tough, but you need to have an idea. Every time you won't be, so easy like they will be on the same line or something. Things can get messed up. So let's say we have a source here, S1, which is 4 lambda comma 0, and we have S2 here, which is 0 comma 3 lambda. So we have a detector, which is, this moves on x-axis. Now they can go mad and they can say the detector is going on this line, y is equal to x plus 1. Getting it? They can play around. So find the number of maximums and minimas detected by the detector. If this guy is going on x-axis from plus to minus infinity, how many maximas and how many minimas will it see? We have two sources, S2 and S1. Positions are given, lambda, lambda. Find the number of maximas and minimas on the x-axis. This is again, first define delta x, S1p or S2p. Anything is fine. First define that. Because without that, you will start getting confusing. Plus minus ka bahut diya ho jayega. Okay, Navya got 9 and 10. 9 max, 10 minimum. Saish got 9 max. Give me both, maximum, minimum. Just don't tell one. So how do we start? Same thing. First, let's define. I'll call delta x as S2p minus S1p. Okay. So now if you send a letter like this and letter like this, at infinity, delta x will be 4 lambda because this is the path difference. Okay. So at infinity, delta x will tend to 4 lambda. Be careful because you can never reach infinity. So 4 lambda is not counted. Next thing, if a letter comes directly and hits here, S1 pe, at this point, the path difference is 5 lambda. Isn't it? And if you go to the left-hand side, here the path difference will be minus 4 lambda. Now, look at the numbers here, how the numbers are going. So if that is minus 4 lambda, somewhere here you'll have minus 3 lambda, here you'll have minus 2 lambda, here you'll have 1 lambda, right? And somewhere here you'll have 0, right? And again, you'll have somewhere 1 lambda, you'll have 2 lambda, you have 3 lambda and 4 lambda, and that is 5 lambda, right? This is 5 lambda and this is 4 lambda, so there is nothing here. There are no maximas on the right hand side. Because just look at the number. You got 5 lambda and then suddenly went to 4 lambda at infinity. So there's nothing on the right hand side. Making sense? You don't count infinities. Infinity you'll never reach. So how many are there? 1, 2, 3, 4, 5, 6, 7, 8. Is that clear, everyone? So there are 8 maximas. Wait, I think I forgot a 4 lambda in the middle. Yeah, 4 lambda bhi hai. So 4, 4, 9 maximas. Yeah. And what about minimas? So here you have 4.5 lambda. So the other numbers 4.5, 3.5, 2.5, 1.5, 0.5, minus 0.5, minus 2.5, minus 3.5. So yeah, how much is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. There are 10 minimas. Clear with this? So there is nothing between, in this region, there are no maximas. There's only one minima there. Any doubts on this? Yeah, great. Next thing, now before going to YDC, right? I hope you have gone through the experiment, but I'll just brief it up. So if you have two slits, S1, S2, and if you take a screen, so this is your x is equal to 0. If you take a point P, if this distance was D, and if the central angle is theta, right? So this is capital D. So we get the path difference delta x is equal to d sine theta. This was done under the assumption when d is much, much greater than capital D, right? And let this distance be x. Then the second assumption, this is your first assumption. So you need to know the assumptions, because if they mess up something with the assumptions, you're gone. Just to be more clear, delta x is nothing but S2p minus S1p is d sine theta. Because if something changes in the problem, this is where you'll always come back to. The second assumption, if x is much, much less than d, that means you're looking at the points very close to the center. Right? And then the theta will be small. And then you can argue sine theta becomes almost equal to tan theta. This is your second assumption. In this case, delta x will become d tan theta, and tan theta will be x by d. That is your path difference. So if you have a point P somewhere on a screen at a distance x, the path difference is given by dx by d. Under the assumption, this is your second assumption. Once you got the path difference, then we will say the phase angle is 2 pi by lambda delta x. Then generally you want to find the intensity, then intensity resultant will be, this is the general formula if your intensities are different, I1 plus I2 plus 2 root I1 I2 cos phi. Clear with the assumptions? So under these two assumptions, the formulas were derived. So let's see a question. S1, S2, the distance between them is 2 millimeters. The wavelength lambda is 6,000 angstroms. We got a screen here very far. Capital D is 2 meters. So there's a point P here at a distance x. Find the intensity at point P. When x is 3 millimeters. When x is 3 meters. Now, at a mains level, you need not care about this. You can just use your regular formula dx by d and you can finish it off. You'll be fine. Advanced mein they'll slaughter you. They will literally check whether you actually understood the derivation. So you should know each and nook and corner, what assumption may what was derived, why it was done this way. So that is the difference. Again, advanced is not really tough. It is like, it should be in and out, should have an idea what you're doing. So still, just now I explained you now, if exam में they directly give x is equal to 3, 99% people will use the standard formulas and finish it off. Just write the equations, don't need to simplify. The numbers might be a little bad. I just wanted to get the idea. Just write the equations and done. That's it. Don't worry about it. I'll give you a minute and then I'll show you both. Let's see whether you got it right. Definitely spend some time on this chapter. It's really worth it. It's not difficult. If you just go through the notes, right? And we have done in the notes little neatly, like, every sequence, what happens, why, and everything. It helps a lot, even for mains and bits also. There are 10 cases. Yeah, the beach mein. We're not going to do it right now, but those are all mains-based questions now. Here. The 15th question, see, there are 10 cases. Different sources have different intensity. They have different wavelengths. Two identical bulbs. Two bulbs can never be coherent. So if you put two bulbs, you will not get an interference pattern. Then we have, instead of light, if I use alpha particles, then what will happen to the fringe with de Broglie wavelength? What if the light comes at an angle, right? What if you have different Slitka sizes? So intensity of the slit is proportional to area of the slit. What if intensity of one slit is increased? This is a good one. What happens if you use white light? White light is actually useful to find the position of central maxima. If you guys remember, that was a standard question, right? And that was one. And then J, what happens if there is a medium surrounding? So yeah, we did a lot of cases. So go through the notes. I keep telling you, notes as a huge collection of questions. So first finish your notes thoroughly and then go ahead. How do we handle this? Let's see the first case. The first case, x is equal to 3 mm, which looks much, much smaller than d. I'll just use my regular formula. Delta x is equal to dx by d. D is 2 mm, 10 power minus 3. X is 3 mm, 3 into 10 power minus 3 by 2 meters. And this is equal to 2 pi by lambda delta. Sorry. So then we get phase angle is equal to 2 pi by lambda delta x. Perfect. For the B case, now x is comparable to d. What happens if x is comparable to d? If x is comparable to d, then this angle is not small. And if the angle is not small, you cannot write sine theta is equal to tan theta. So your path difference delta x is d sine theta. This is still valid. But what is sine theta now? Your sine theta will be dx by root over d square plus x square. Is that clear, everyone? You cannot use a dx by d anymore. Once you got that, again, story is still the same. Once you got the path difference, actually the question gets over. And what is the intensity at point P? 4i cos square phi by 2, because both are same intensity. Clear with this? So if you know that x is big and you can't use the formula, there's nothing in the equation. But in the exam in a hurry, right, you won't realize. So you see x is equal to 3 meters, so you'll not think much, you'll go ahead. Let's see one more like this. Lambda 6000 angstroms, and let's say this is 2 millimeters. I'm keeping the number same. Let's say this is 2 meters. Find the position of 5th, 50th, 500th, and 5000th maxima. Exam with, I think I'll give you 500th maxima directly. And remember, you see a number like that, right? 50, 500, it's a trap. If you see single digit, it is okay. Just use your regular stuff and finish it off. Third maxima, 7th maxima, 10th maxima is also fine. The moment you hear numbers like 300, 400, you should be thinking, boss, kuch to gadbad hai. Let's see how will you handle this. Try, take 2 minutes. And just to give an idea here, in this formula, fringe width, lambda capital D by small d, this is valid only if x is much, much less than d. If you go really far away from the screen, fringes will not be uniform. In case you guys remember, this is how the fringe pattern will look. Dekho. This is a vertical thing. I'm showing you horizontal. This is how the fringes will actually look on a screen. Can you see here? Here, the fringes are uniform. So basically, this is a distance where x is much, much less than d. If you go here, this is x is comparable to d. So here, the fringes are uniform. They are equidistant. If you go very far, fringes will spread out. So if you go far from the screen, because that formula lambda d by d is derived under the assumption that x is much, much smaller. This is not equal to lambda d by small d. If you are very far. So they can ask something like find the distance between the 300th and the 301th fringe. That will not be lambda capital by small d. Okay. Right, Janet. Get the remaining though. Sorry, this is a question. 5th, 50th, 500th, and 5000th. Could be a more than one choice question. Who knows? If they're in a little merciful statement, this could be a paragraph. Again, don't think advanced matlab everything will be out of the world. If you notice the papers, half of the paper every year is solvable. They'll be like 20-30%. Sometimes they'll go crazy. So what's the catch? So when you look at the fifth maxima, so I will assume x is small and I'll solve the problem. Delta x is dx by capital D. D is 2 mm. 2 into 10 power minus 3. X, okay, we need to find that. So delta x is equal to 5 lambda. N lambda, no? Fifth maxima is 5 lambda. So this is 2 into 10 power minus 3. X by capital D is 2 meters. This is 5 into 6000 angstroms. That is 6 into 10 power minus 7. 6000 angstroms now. So yeah, 2 cancels. So we get x is equal to 30 into 10 power minus 4 meters, or x is equal to 3 mm. Make sense? Now, is x is much, much less than d? So you can clearly see x is much, much less than d. So my assumption was right. I can use this formula. So you have to solve the question under the assumption, then you check. Let's go for 50th maxima. Or you can directly use a d sine theta also. So, but I'm just trying to show you. So if I do the same logic here, dx by d is equal to 50 lambda. When you solve this, you'll end up with x is equal to 30 mm. Do you think this is still smaller than that? Yeah, I think it still looks smaller than this. So yeah, this is also almost right. If you even use d sine theta, you'll get an error in third or second decimal. But if I go for 500th maxima, then you'll get x is equal to 300 mm or 0.3 meters, isn't it? This is not small. Now x is comparable to 2 meters. That's an error of almost how much? 15%. So delta x is not equal to dx by capital T. Actually, you can use d sine theta from the beginning and do it. It will be little work, right, Arsh? And then delta x will be d sine theta, and your d sine theta will be d into x by root over d square plus x square. This is equal to 500 lambda. Got it? Now you can substitute 2 into 10 power minus 3 x and d square and x square. D square is a 4 plus x square. Root is equal to 500 into 6 into 10 power minus 7. 1, 2, so this would be 30. Right, so that will be 3000. So 3 into 10 power minus 4. And there's a 10 power minus 3. So this is 0.3 by 2. x by root over 4 plus x square, square on both sides. That would be 4x square. Please check your calculations. I'm just rushing something. 4 plus x square. Yeah, this is doable. You can solve this. You'll get x is equal to something. Clear with this? Look at the 5,000. It doesn't exist. So generally when the number exceeds 1,000, right, you can verify and see. You can use that method which I just taught you. So S1, S2. So if you go exactly and meet in the center, the path difference is 0. But if you go parallelly, at infinity, the path difference delta x will tend to d. That is the distance between them. So if delta x is 2 millimeters, and if this is equal to n lambda, so this is 2 into 10 power minus 3, n, and lambda is 6 into 10 power minus 7, then you get n is equal to 1 by 3 into 10 power 4, or n is 3333.33. That means at infinity, the number rate starts from n is equal to 3333. Isn't it? So the numbers will go from n is equal to minus 3333 to 3333. So 5,000th maxima does not exist. And they can ask you this question: how many maximas are there? 6,667 maximas exist. Clear with this? So n is equal to 5,000 will not exist. Is the idea clear there? Because the number has become so big, it just literally that number doesn't exist there. So that is the thing. You have to be careful. Always check whether that x is small or not. So if you don't understand that, what people will do, they will write 5,000 into lambda capital D by small d, and this option will be there. And the best part, this doesn't exist. I hope you're getting the catch there. All clear with this? Now, in YDAC only, what if, no, this is the thing, huh? So YDAC, you learn this, you know what are the assumptions, and you keep playing with that YDAC. You keep messing up one after another. So this is your another variation. Let's say we have two slits. We have the screen S1, S2. Let's say the source is here, not on the central line. Let's say this is 2 mm. Let's call this thing D1, which is 3 meters. Let's call this thing D2, which is 2 meters. And let's say this is point P, which is 3 mm. Assume the intensity of S1 has to be same. Find the intensity at point P, or find the path difference at point P. So this is a case where the source is not symmetrical. So now you're messing up the source. The source is not symmetrical to S1 and S2. It is 2 millimeters above them. What is the D? DB chahiye na? You can take this thing as maybe 3 mm. We'll do one thing. Just let's take in variables only. Small d. Let this be y. Let this be x. Let this be y. D1, D2. Give me answer in terms of this. Assume x and y are small. If I don't say anything, they're small. So, there. So what will you do if the source is messed up? The source is not at the symmetrical thing. So there are a lot of variations there. What if that x is small? What if that, small d is big? You can even do that also. If capital D and small d become comparable, that approximation only goes off. D sin theta becomes wrong. How do you handle this? Very well. We had to use approximation 2 times. Think for a minute. Okay. Now, let's ask yourself, what are you exactly trying to find? You want the path difference till P, isn't it? So what is happening is one light ray is coming to S1 and going to P. One light ray is coming like this and going like this. So what you're trying to find, the path difference is S S2P minus S S1P. This is what you're trying to find, the path difference between these two. Now I can write this thing as S S2 plus S2P minus SS1 plus S1P. This can be split into SS2 minus SS1 plus S2P minus S1P. Okay. Now, end of the day, think of like this. So this is S1, this is S2, this is the source. Can I still do the same approximation? So if I drop like this and if I drop a perpendicular, this is your extra path difference, isn't it? And if you take this angle to be theta, this angle to be theta, so this extra path difference will be how much? D sine theta. So here the path difference S2S minus S1S will be D sine theta. Since x is small, for small angles, d sine theta can be written as d tan theta. And this will be nothing but dy by capital D1. Make sense? The same thing you will, that's what we did in YDSC. So the S1, S2, this is point P. Same story, you're dropping a perpendicular. This is, let's call it some theta dash. This will be theta dash. So here the path difference S2P minus S1P is d sine theta dash. For small angles, we can write this thing as d tan theta dash. And this guy will be dx by capital D2. Make sense? So just separate them, treat them like two YDCs on left and right. And then you're done. So what is the part difference? So if you realize like this, dy by D1 plus dx by D2. Once you got the part difference, the phase angle will be 2 pi by lambda delta x, and yeah, you'll get everything you want, intensity. Clear this thing. Clear? So if you move the source, this is what you do. Again, the source has to be moved small distance. Neto, you can't do this approximation again. Yeah, it's like a double YDC kind of thing. So you're doing path difference for the left and the right. Clear with this? Take a break. Come back in 5 minutes. We'll continue from here. So we will keep messing up this YDC more. We'll keep adding, changing stuff. Sure, let's go ahead. Before doing the actual one, let's see how much you remember this one. S1, S2. Let's say you kept a slab in front of it. Thickness T1, mu1, there's a slab in front of it. T2, mu2, right? Yeah, and lambda vacuum is lambda. This is point P. Find the part difference at point P. Now, in case you're confused, just to give an idea there, if you have a slab of mu, and let's say the thickness is D, and if you send a light ray inside, the time taken for this light ray is D by C by mu, which is mu D by C. That means the same light ray, if it's trying to travel in vacuum, right? Let me do even something better. Wait, this is mu slab, and let's say surrounding is mu medium. Okay, so mu slab D by C. So if you want to replace this slab with the surrounding medium mu m, and we are trying to say the time taken by the light ray must be same. So that is the optical path ka definition. If the time taken by two light rays is same from A to B, then we say both of them have same optical path. Right? So here, if the light ray travels here, so here the time taken must be D dash by C by mu medium, which is mu medium D dash by C. And when you equate them, mu slab D is equal to mu medium D dash. So we get D dash is mu slab by mu medium into D. That means you can replace a slab of thickness D, which is surrounded by a medium. If it is vacuum, then mu1 ban jayega. So you can replace this with an equivalent slab of mu m, whose thickness will be that formula. So clear with this idea there? So that is the same logic here. So whenever you pass through a slab, right? So if you have a slab of thickness T and mu, right? So the path difference will become mu into T. So what is the extra path difference? If the slab had not been there, you would have traveled a T distance. Because the slab is there, you have traveled a distance mu T minus T. So T into mu minus 1. Is that clear, everyone? Yeah, if you're covered with medium, then it would have been mu slab by mu medium into T minus T. So this is the actual formula. So whenever you pass through a slab, the extra path difference it creates is mu slab by mu medium minus 1. Clear with this? The mu medium is the medium present in this whole thing, whatever it is. Then, so light ray will go like this, the light ray will go like this. The story is the same. So what is the path difference? S2P plus, because you're going through a slab, you'll have an extra path difference T2. Here it is vacuum, so I'll just say mu2 minus 1. minus the light ray S1, you're going from S1P, and because you're going through a slab, you will feel you have traveled extra distance T1 into mu1 minus 1. But we know S2P minus S1P is dx by capital D plus T2 into mu2 minus 1 by T1 into mu1 minus 1. This is your path difference. Clear with this? If I put delta x is equal to 0, I will get the position of central maxima. So they'll ask you by what distance is the maxima shifted and everything. Clear? This is how you derive the formula. Meaning I actually don't remember this. I always derive this. You can derive it easily. Clear with this? This is your standard concept. All clear with this? Now let's see the actual question. S1, S2. The source is here. Let this distance be y. This is p. Let this distance be x. Everything is small. You kept a slab in front of it. You kept a slab in front of it. This is mu1, T1. This is mu2, T2. This whole region here is filled with medium mu3. Wait, I'll do even something better. Let the slab be here, mu2 and T2. And this whole region here, left side, is filled with mu4. You're getting how is the medium there? The entire left-hand side is mu4. The entire thing between the slits and the screen is mu3. The one slab is here and one slab is here, and the source is above the center line. There, we can mess up big time. Find the part difference at P. Lambda vacuum is lambda. So the biggest confusion comes here, like when you have already four mediums here, mu1, mu2, mu3, mu4, like how do I even start? So that is the biggest confusion that every time you face with. So the idea is this. So listen to the idea here. The idea is convert everything into vacuum. Calculate all the part differences and convert all part differences into vacuum. How do you do that? If you have a slab of mu and thickness d, this can be converted into a vacuum. So if the part difference is d in a medium, then in vacuum it is simply mu d. That means if you travel distance d in a slab of mu, it is as good as traveling a distance of mu into d in vacuum. Are you getting the logic? If a light ray travels in a slab of distance d, it is as good as saying it has traveled inside a vacuum of mu into d. A ray traveling d in a medium is same as a same optical path of a ray traveling in mu d. So basically the optical path of that light ray is mu d. Let's see how you handle it. I mixed up a lot of things. Let's see how will you put one after another. Listen carefully. Yeah? So we are taking light rays. So one ray, and use some black. So this guy goes through S1 and then it goes like this. This guy goes here and then goes like this. Okay? Perfect. So the first thing. So what you want to find is SS2 and SS1P, but again, be careful here. When you go from S to S2, you are traveling through a medium. You're not traveling through vacuum. So what medium are you traveling? So we are converting the path difference in terms of vacuum. So again, same question. When you travel from SS2 in mu2, in mu4, it is equal to traveling a distance of mu4 SS2. Is that making sense? If you travel in a medium mu4, a distance of SS2 that is equal to traveling in a vacuum mu into SS2. Agreed? Plus, because you're traveling inside a slab, you will get an extra path difference, right? How much is that? That would be T2 mu2 by mu4 minus 1, but this is the path difference in mu4. So again, you have to put one more mu4. Because this formula, when we derived here, this is the path difference for a slab, which is equal to the medium, isn't it? You have to convert that medium back into vacuum. Clear with this? So this term is the path difference with respect to the medium. That means because of the slab, it feels you have traveled this much distance in the medium. But again, remember, you're converting everything into vacuum. So you just have to multiply mu4 to convert everything into vacuum. Plus, then you're going from S2 to SP. The medium is mu3 into S2P. This is one big term. This is the light ray from S2, S2 and P. Minus, you're going mu4 SS1. यहाँ पे slab नहीं है, so you're safe. Then we have mu3 S1P. Here you have a slab, which is T1 mu1 by medium is mu3 minus 1. But again, same story. This is the path difference in mu3. This is a mu4. So this term here is a delta x due to slab in mu3 medium, but I don't want mu3 medium. What I want is mu, the surrounding medium. So into mu3. There. This is your path difference. Please have a look at this. Are you getting what we did? Maybe to give you an example, I'll do one thing. Wait. Same question, if I had given like this, maybe you'll see the difference then. Let's say if I say this is right mu dash, and let's say this is also mu dash. Both the sides, the medium is same, right? And if you're going to put a slab here, and if you're going to put a slab here, now I will not do everything in vacuum. Everything is mu dash, right? I don't have a problem. The light ray is always traveling in mu dash. So I will find the path difference delta x in mu dash. So the medium has to be mu dash. So now I will say SS2. Where did you travel? SS2 travel in which medium? Mu dash. So I have no problem. The slab ka path difference is T2 mu2 by mu dash minus 1. Where is this path difference? In mu dash. No problem, because you're finding path difference in mu dash only. Plus S2P. Where is S2P? In mu dash. So I'll not write S2 dash. Minus, right? And then this would be SS1 plus T1 mu1 by mu dash minus 1 plus S1P. If everything the medium is mu dash, this is how the equation would have looked. This is a delta x in vacuum. So if you want to convert this delta x in vacuum, that must be mu dash into delta x in mu dash. Means if I multiply this whole formula with mu dash, I will get the part difference in vacuum. समझ में आ रहा है? And if you multiply mu dash, now you can see actually, isn't that this mu 4? Please understand this six terms. Huh? I'll give you a minute. Have a look at the six terms. If you got this, you actually understood a lot of concepts. So whenever you have mediums changing like this, light rays going from one medium to another medium, it becomes really confusing to what to do. So best thing, सबको एक ही formula लेके आ जाओ. Convert everything into vacuum. So this entire part difference you got must be equal to whatever you want to do, n lambda. So n lambda, but be careful, this should be in vacuum. Sometimes they'll give you the wavelength in the medium. You have to convert that into vacuum. And then, yeah, you'll get whatever you want. You want central maximum, put delta x is equal to 0. You want first maximum, put 1 lambda. You want minima, you'll get lambda by. You'll get everything. And and what are the values there? You still, this thing, right? SS2 minus SS1. You know this thing. How much is that? dy1 by d1. S2p minus S1p is dx by d2. This we did in the previous question. So you actually know everything here. All clear with the six terms? Any doubts on this? This is a good one. Should definitely go through this thing. So I can actually keep 4 slabs also. But again, it just becomes lengthy. You got the idea there. All clear? Great. The next thing. So we have a medium here. This also we did in the class notes. It's a good one there. The one side of the medium is mu1, the other side of the medium is mu2, and the mu2 is greater than mu1. You can take this point as origin, and you can take this point as some f comma 0. It is observed when you send parallel light rays, all these light rays bend and they meet at this point. Find the equation of this interface. So this thing, this curve, find the equation of the interface, what shape it is. I want the equation. Now don't say parabola. That is what, if you have a parabolic mirror, the light rays reflected on a parabolic mirror will meet at the focus. This is refraction. Getting it? So don't mix up that with this. So you're sending parallel light rays from infinity, and all of them, after hitting this interface, they meet at the focus. This happens for a particular equation of that curve. What is that curve equation? The idea is this, okay? Since the light rays are coming from infinity, right? And when they're meeting at one point, the path difference must be same. The time taken for all the light rays from infinity to f must be same. That's why they're meeting there. Now go ahead. I'll give you one more example. Listen, when you take a lens, think about this. The light ray from here will go straight. This light ray will come here, but both the light rays meet at the same time. How is that possible? Because this light ray, even though it travels shorter distance, it will travel more inside the thickness of the lens. So it will slow down a lot. The light ray which is going here will travel less time inside the slab. So even though they're traveling different distances, the time taken for both the light rays will be same. So in a lens, all the light rays going from object to the image have same optical path. So in order to form an image, they should meet at the same point at the same time. Making sense? So all the light rays, when they go from object to image in a lens, have same optical paths. How do you do this? You get something like this. This will actually form an ellipse. Little bit of geometry there. It's not really that thing. Let's see. So consider this point here, A, B, F. So let's just consider only two light rays. Okay. And let this point be x comma y. So we are trying to find the equation there. So we have one light ray going straight. So there. So that means this time and this time is equal. Okay. So the time taken from A to B to F must be equal to time taken to go from O to F. That is the idea there. So time taken to go from A, B, F must be equal to time taken to go from O to F. So this will be AB, C by mu1. This is B to F, C by mu2 must be equal to O to F by C by mu2. So indirectly, if you see, there's a path difference only. See, mu1 into AB, that is a path difference in vacuum. Mu2 into BF, that is a path difference in vacuum, must be equal to mu2 into OF, that is a path difference in vacuum. So the total path difference must be same. So optical path is same. So A to B will be how much? X. B to F will be how much? Drop a perpendicular. This would be F minus X. So this will be root over y square plus F minus X whole square, and mu2, this will be F square it on both sides, mu2 square y square F minus X whole square is equal to mu2 F minus mu1 X ka whole square. Simplify this, you will get an equation. So this would be an ellipse if mu2 is greater than mu1. If mu2 is less than mu1, it becomes an ellipse, hyperbola. So that thing is important. So the coefficient will come something like, I think Navya got an answer. Mu2 square minus mu1 square x square plus mu2 square y square is 2xf mu2 square minus mu1 mu2. So yeah, that's the answer it seems. So you can check. So this is a hyperbolic ellipse equation. Clear with this? There'll be another mu1 term. Yeah, check it out. So there'll be another mu1 term. Why there'll be another mu1 term?
Because mu1 से mu2 transition हो रहा है.
No, we are finding distance from
by
O to
C. OF by mu1 C by mu2.
why?
Because
Oh, God, we are finding time taken, right? Distance by speed.
we are converting our vacuum itself.
We're just using time, no? We convert everything in vacuum only. All clear with this? So this is one good one. Next thing. Thin slabs, huh? This is another important one. Now, the standard model was this, okay? The standard model was you send the light ray almost along the normal. So one light ray will go inside and will come out. The other part of the light ray will get reflected from here, and then you do interference of these two. But if you see, there was a case where if the light ray hits at an angle, I think it's a little too big of a derivation. I'll just show you. Have a look at this. So this is the first thing that you should know actually. Thin film interference, you should definitely check it out. But yeah, let's see. I think we will do it. So we have a slab here of thickness D. Now let's say if a light ray is incident on it, see every time a light ray hits a boundary, two things happen. You get a reflected ray and you get a refracted ray. So this is I, and this is R. When this thing hits here, again you'll get a reflected ray and again you get a refracted ray. This will become again I, and this is R, and this is R. When this thing hits here, again you'll get a bouncing here and you'll come out again here. This will be again I, and this will be R. When it hits again here, it will bounce again. This will just keep going on. So just to name them, if I call this thing as ray 1 and if I call this thing as ray 2, If I call this thing as ray 3 and if I call this thing as ray 4, okay? And if that is angle I and that width is d and this refractive index is mu. Can you find the path difference between 1 and 2? Get this thing. Find the path difference between ray 1 and ray 2. Try. I'll give you a minute or two. So if your light ray hits at an angle, you'll always get a reflected ray and a transmitted ray. So this will just keep on happening inside. Find the path difference between ray 1 and ray 2. Both will be parallel. So then what they do, they actually put a lens here. These two light rays will hit the lens and they'll meet at the focus. So by adjusting the angle, sometimes you'll get bright spot here, sometimes you'll get dark spot here. So whenever you get a bright spot and dark spot, it's a maxima and minima. So from there, you can actually find the thickness of the film. So this is an experiment to find the thickness of thin films. So this is the technique you use when you want to find thickness of films, which is 1 micrometer. You can't use any instrument, they will break. Do you guys remember this picture? This is an oil on water surface. Ever observed when oil falls on a water surface, you get these colors? This is actually interference pattern. The oil will form a thin layer on top of the water with different thickness. So at a particular thickness, red will form a maxima. At a particular thickness, red will form a minima. So you will see wherever you're seeing blue color, that is blue ka maxima, but red ka minima. So you have different colors there. So this thing which you see oil in a water surface is an interference pattern. Anyway, let's get this. Get me in terms of I and R only, okay? I know you can calculate I and R, Snell's law. So get me the path difference in terms of D, small I, small r, and mu. So yeah. It's a bit of a geometry. Wavelength lambda. First thing I'll ask you one thing. Tell me what is this? Suppose if this light ray ka phase angle is 0, can you tell me the phase angle of all the remaining rays? Now this thing comes from waves. If you guys remember, if a wave is going from a light string to a heavy string, that is rarer to denser, what will happen? If this is phase angle 0, the reflected ray will get a phase angle of pi. It gets inverted. The transmitted will be always in phase. Yeah. So when you go from rarer to denser, how do you define rarer and denser? If the wave is going faster, it is called rarer medium. If the wave is going slower, it is called denser medium. So this is called optical density. It depends on the speed. Similarly, when a wave goes from a thicker to a thinner, or in this thing denser to rarer, the reflected and the transmitted both will be in phase. Clear with this? So check it out. So who is rarer and who is denser here? Vacuum is rarer, you go faster there, and this is denser. The idea important. They can put one more sheet here and they can mess up the whole problem. So you're bouncing off rarer to denser. So this will have a phase angle of pi. Agreed? The one who's transmitted will have phase angle 0. This guy is also transmitted, phase angle 0. Here you're bouncing from denser to rarer. So reflected will also have a phase angle 0. This will also have a phase angle 0. This will also have a phase angle 0. This will also have a phase angle 0. Check. This is the only guy with a phase angle. Remaining all will be 0. That means because the light ray bounced off, just because of bouncing, you'll get an extra path difference of lambda by 2. Clear with that? Now comes the geometry. So you want to find the path difference? Fine. So look at this thing. So this ray 1 starting from this point, okay, it is traveling this distance. Fair enough. The ray 2 is going inside, then it is going this way, and then it is coming out. So from here, if you drop a perpendicular, so for simplicity, I'll just put some alphabets here. Let's call this thing A, B, C, and let's call this thing D. So the path difference between ray 1 and ray 2 will be you're traveling A to D plus lambda by 2, that is because of reflection, minus this guy will be mu into, because you're traveling in the slab, AB plus BC. Is that clear, everyone? The green one is traveling inside the slab. So I'll just choose the same colors, mu into AB plus BC. Are you getting the path difference? Ray 1 and ray 2 both start from point A. This will reflect and this will go inside and this will come outside. So the path difference is up to point D. This is your path difference. And if this is I, this is I, this is 90 minus I, and this is I. You can calculate. Yeah, now it will be all calculations there. AD is equal to AC sin I. And if you drop a perpendicular here, if this is R and R, so you can calculate this. So if you call this point as E, AE will be D tan R or something. Tan R is equal to D by AE. So AE will be D by tan R. This is equal to EC. So you can calculate it. It's just all lengthy after this. Once you got that, you will get it. The path difference lambda by 2. Do we have to take mu refractive index? No, Arush, because see now, where is this reflection happening? It is outside, right? It is in vacuum. Right, Arush? So the reflection is because of the thing, right? Lambda by 2. That has nothing to do with the medium. Whenever you hit from a denser to rarer, you get a path difference of lambda by 2 in that particular medium. It's coming from which medium? Vacuum. So it's a path difference in vacuum. Clear with this? Suppose अगर बाहर का medium mu3 होता था, then yeah, I would have done mu3 also here for the whole thing. Clear, Arush? Clear with this? So there are a lot of things in this. You should definitely go through the notes in more detail. Look at this thing. So this is called reflection interference because this is coming from the reflected rays. Similarly, ray 3 and ray 4 will also have a refraction interference. Now, luckily, there's no need to do everything. It's easy for refraction. So there, this was the derivation. You can check it out. So the light ray will travel AD plus lambda by 2, and this light ray will travel mu into AB plus BC, solve them. Then we simplified this. We got a big deal like this. So this is the path difference, 2 mu D cos R minus lambda by 2. Construct interference, destructive interference. We prefer to study destructive interference because it is easy to see. So now this is the logic for the other one. Huh? Listen to this thing. If you see the difference here, look at everything, calculations. This thing has a pi, this thing has a 0, this thing has 0, and this thing is 0. If you look at the difference, the only difference is lambda by 2, isn't it? So if you can calculate for 2 and 1, 3 and 4 may just lambda by 2 nikal dena. That is the path difference for the refraction. But there is another way to get this thing. Huh? Look at this. If you have two people standing on both the sides of the screen, the red guy and the green guy, if the red person thinks there is a constructive interference, then the other guy will think it's a destructive interference. Always. If this guy thinks it is dark, then this guy will think it is bright. Why? Conservation of energy. If one side you get a constructive interference from conservation of energy, the other side should not have any energy, isn't it? You cannot have constructive on both the sides. You cannot have destructive on both the sides. To balance the total energy, if one person sees constructive, this guy will see destructive, and vice versa. Clear with this? And if you put I is equal to 0, this is your special case, which we actually do at mains. If I is equal to 0, then R is equal to 0, then your formula becomes really nice, 2 mu d minus lambda by 2. And then it is easy to solve. 2 mu d minus lambda by 2, and then you can finish it off. Make sure to go through the thin lens. This is not difficult, but yeah, you should know that. So if I have to give you a question on this, I'll just leave it here. You can refer this. You should go through the wave optics converts. The whole thing is a pretty good one. Page 106. Tell me about this guy. Let's say we have a slab. This is 2 mu, this is mu, and this is 3 mu. And light ray, right, is almost coming at an angle 0. So this is the light ray. So one light ray bounces off like this. Another light ray enters and comes off like this. And so we can say I almost tends to 0. Lambda vacuum is lambda naught. Can you find the path difference between ray 1 and ray 2? So you can assume light rays are just traveling vertically. Okay, so you can ignore all the angles. Whenever you see multiple mediums, you get confused, convert everything into vacuum. Get all the part differences, convert everything into vacuum. Or you can convert everything into 2 mu cum medium. It works either way. So first thing, you need to be clear who is rarer and who is denser. So between 2 mu and mu, this guy is denser. This guy is rarer. This guy is rarer and this guy is denser. Perfect. So after the first bounce, you're hitting from denser to rarer. So there'll be no phase shift for the first one, 0. So blindly, if you put every time lambda by 2, you'll get trapped. You need to see who is rarer and who is denser. This green one is traveling inside. So path difference will be mu into d. So mu into d, that is in vacuum. This is also mu into d. And don't forget, here you are bouncing from rarer to denser. So that will create a path difference lambda by 2. And when you come out, again, you won't have a path difference. So the path difference between the red one and the green one. So the path difference for the green one, it will be mu d because you're traveling in the slab, lambda by 2 because of reflection, plus mu d, you're traveling in the slab. right? And minus 0 that time, right? So yeah, done. And that's your part difference. Again, remember this is in vacuum. Clear with this? There is one more thing, beta. What is this lambda exactly? This is the lambda in the slab. That is not lambda in the vacuum. Because if you're reflecting inside, the wavelength has already changed, isn't it? The wavelength will be lambda slab. So this will be 2 mu d. What is the lambda slab? Lambda by mu 2. Lambda slab will be lambda by mu, lambda vacuum by mu. Because the frequency remains same, the speed will change. Clear with this? So in whichever medium you're bouncing off, uska lambda by 2 aayega. So there is one thing, be careful with this. Clear with this? Now, based on this thin film, right, they have some weird questions also you can get. So like this. I hope you guys remember that one, the thin film wala. So we have a thin slab here. This is theta. X is equal to 0. This is x is equal to some t. Right? And theta is very small. I'll show you one. So they'll ask questions like this. They will say a parallel light is shined onto it. So ये questions में क्या होता है ना? So when the light comes and hits here, you'll get one light ray will bounce off. The other light ray will enter inside, will come and will come out like this. So we'll assume it to be a very thin parallel slab. So let this distance be x. Then this distance will become x tan theta and x tan theta. So we'll assume this distance is x tan theta. X tan theta. Okay. Same story. So this guy will have a phase difference of you're hitting from what? Air to glass. So this will have a path difference lambda by 2. This is denser to rarer. So this will have a path difference of 2 mu x tan theta. Then it comes like this. The path difference will be 2 mu x tan theta. Theta is small, so you can make it as theta into lambda by 2. Then the question comes like this. Find the number of maximas on the screen or on the base. This should be equal to n lambda. But we know x ka value maximum is t. So n ka value will turn out to be 2 mu t tan theta minus lambda by 2 by lambda. So this will become the n. So this is the total number of maximas. The total number of fringes. So what is happening exactly? I'll tell you. See, what is happening here is, so the light which falls here, this will travel different distance, isn't it? The light which falls here will travel a different distance, different distance, different distance, different distance. Can you see what is happening there? Path difference बढ़ रहा है ना? So there will be a point where the path difference is 1 lambda. There will be a point where the path difference is 2 lambda, 3 lambda, 4 lambda, 7 lambda, 8 lambda, so on. You're getting it? So the question is how many maximas are forming? So once this thing ends, then let's say at this point you got 7 lambda, then the maximas are 7 maximas. Clear with that? So they can frame questions like this by putting thin slabs. Another variety of questions, right, on this thin slabs is this. Let's say they kept a sphere. Now, when you see different shapes, now don't get scared. The idea is always this. You have to convert every problem into a thin slab, right? Even though this is not a parallel slab, because theta is small, you can actually assume this shape to be like this and solve the problem. Is the logic clear? So even if I give a weird shape like this, here also we'll do the same thing. We will assume this to be a thin slab and we will take this is a thin slab and we'll do the problem. The idea is always the same. So we have a hemisphere, glass hemisphere on a floor. And someone started shining light, from the top. a parallel beam of light. And let's say this distance is x. X is much, much less than r. So you're sending it very close to the center. Right? And then they'll ask you, find the number of maximas. So this distance is up to x. How will you find? What is the shape of the fringes? So the question would be find the number of maximas. The refractive index is mu. So parallel beam is incident. This is also a kind of a mirror kind of thing. Along the center, very close to it. So the main idea is somehow to get the path difference. So this, I just exaggerated the figure a bit. So let's say light is coming from here. It goes straight. This will bounce off. The other part of the light ray will come out, hit the mirror, and will bounce off again. So it's something like this. So we have to assume that thing is like a small thing there. Let this distance be t. We can use geometry. This is x. This is r. So this is root over r square minus x square. So t is nothing but r minus root over r square minus x square. That is your t. For the green one, what is the path difference? 2t, because you're traveling in vacuum. This is vacuum. Plus lambda by 2 because of mirror car reflection. Whereas for the red one, delta x is 0 because you're hitting from denser to rarer. So therefore, the path difference between the red one and the green light ray is 2t plus lambda by 2. But what is t? 2 into that value, r minus, since r is very, very small, I can use binomial approximation. This would be r minus r, this will be 1 minus x square by 2r square. R will cancel, you end up with x square by 2r square. That's your small t. I hope that is right. Yeah. So this will be 2x square by 2r square plus lambda by 2. This is the path difference of a light ray which is hitting at r. So yeah. And what will be the shape of the fringes? So the thing, right, if you see it is depending on the Tika thing there, you'll get the fringes in circles. That's how you handle this. So if you want to find the first minima, second minima, you can put the values of x and you can finish it off. But got the idea there? Every time this is what you play with. You make it as like a thin thing and you do it. You can have different shapes, spheres, triangles, and everything. End of the day, you have to make it like this. Go through the notes. We have done notes में एक और variation किया था. If you see, so there were like a glass slab and a glass slab with a ball in the middle. So you can check it out. That is also something similar. Yeah, so that's a bit about it. Like again, I'm saying, go through the class notes. We had did almost 20, 25 problems. Kiya. We had different models and a lot of varieties there. That should help you a lot. There is one important thing I forgot. Fresnel. There are two experiments in this thing. Experiments are very important for advanced. Fresnel biprism experiment, and one is your Quincke's tube. Yeah, I hope you remember what is Quincke's tube. So what is Fresnel biprism experiment? I'll just brief it up. So You should know how to derive it, derive it on your own again. So in the Fresnel biprism experiment, we take a thin lens, thin prism of angle A. So A is very small. So when you put an object here, the light rays will hit the prism and they'll go like this. So we will assume as if these light rays are coming from a point here, I1, S1, exactly on top of the object. Similarly, this light rays will bounce off and go here, and we will assume this is coming from S2. So S1 and S2 will act like two coherent sources. So this light ray, this is your deviation for thin prisms, is A into delta minus 1. That's your deviation for thin prisms. This can be taken as delta by 2, and this can be taken as delta by 2. This distance you know A, and this distance you know is B. So this distance will turn out to be 2A tan delta by 2. So the final thing becomes like S1, S2. The distance between them is small d, which is 4A tan delta by 2. This is the screen. This is your capital D, which is A plus B. Then you can find the fringe width. This is your Fresnel biprism experiment. You will get questions on this, maybe a variation of this, but this is one and Quincke's tube is one. Again, we have done this also in the notes. You should definitely check out these things. This is the Quincke's tube. Just read it. It is very easy. Because why yoga? Dekha, when I said Quincke's tube, some of you know, but some of you are like, what the hell it is? So exam they'll say like that only. In a Quincke's tube, this happened, solved. And you're like, what the hell? And questions are so easy. This is the Fresnel biprism experiment. I wrote it in more detail. You can check it out. Okay, so that is one. Okay, with that we'll wrap up for the day. So I'll see you guys on Monday again. We'll continue on the next one. What is the next one? Next one is capacitors and current electricity. Quite an important thing. So please make sure to go through the notes, especially check out that potentiometer derivations. Potentiometer is not there for mains, but it is there for advanced. Potentiometer ka circuit, right? A Wheatstone bridge, all that, Meta bridge, especially the experiments. If you don't want to see anything else, at least study that part and come. Very important, that is one. Okay, with that we'll wrap up for the day. I'll see you guys on Monday. Whatever is the schedule according to that. Monday, what is the schedule? Yeah, 6 o'clock as usual. And we'll also have a test on that day. So yeah, any doubts, anything else, please stay back or else you're free to leave. So